Test, sound, test. Good morning, everyone. Welcome back to Chem 1. We are going to do a midterm bonus question this morning. So we'll ask you an iClicker question that was missed on the exam by most of you, over half of you. And you'll be able to work on it with in your small groups, get the answer and record your answer with your iClicker. So we will test the iClicker first. So what we're going to do is we'll do a little bit of the material this morning. We'll do one chem quiz, make sure the iClicker is working, and then we'll do that one just so we have a practice run through. I'd also give people time to join and join in on that midterm bonus if they're sleeping in. So last time we were talking about formal charge, and formal charge is kind of a made up thing. It's a mathematical thing that we do for a relatively specific reason. The charge on a molecule ion can be assigned to one of the atoms, and it's difficult to see where it should go if you just draw the Lewis dot structure. So this is a negative charge. Can we assign the negative charge, or can we assign charges to every atom that just add up to -1 in total? And we do it because it helps us distinguish between the quality of our various Lewis structures and helps us pick the best one. So we talked about this at the end of last time. When we're doing formal charge, we draw the Lewis structure, and then we do kind of a covalent dividing of the electrons. So we divide them up between all the atoms by sharing them. So what we have here is we say, well, here's how the atoms, here's the electrons the atoms have around them in the molecule. And how did we arrive at that? Well, we shared those 4 equally between the oxygen and the nitrogen. So sharing of those 4 in that bond. And we shared these 2 equally between the nitrogen and the oxygen. And then we can count up the electrons, 6 here, 5 here, and 7 around that oxygen. To come up with a charge, we just compare that to the normal valence electrons that they have. So we can look at the periodic table. Oxygen, 6 valence electrons, nitrogen, 5. And then you can see in the molecule, this oxygen, the way we've drawn the structure, has the extra electron around it. It's where the charge might reside. So there's a formal charge on the oxygen. It has an extra electron. So it has a formal negative charge. These two atoms have the same number of electrons that they would if they were just had their valence shell. So their valence shells aren't altered in this division of electrons. So it's just a formalism. The importance is these numbers say, can I use that to distinguish between Lewis structures that are similar? And the rules are basically you shouldn't have high formal charges. So there shouldn't be very many formal charges. They should be on the more electronegative element and not distributed all over the molecule. So as you move electrons and you put different bond pairs in, that changes these formal charges, and you can just check them to see where you're at. So let's look at that in the form of a Chem quiz. Well, we did this one last time, so we'll just run through this one. So we said, let's calculate the formal charge when I oxidize. I add another oxygen there, and you can see how I'm sharing that one, and those two for that nitrogen to get that 4 around nitrogen in the molecule. Atom, it's always the same for nitrogen, 5 valence electrons. So that's an increase. It was 0 here, and it increased in formal charge. So now you have a +1 formal charge here. That means one of the oxygens has to have a -1. Actually, 2 of the oxygens have to have a -1 formal charge, because the formal charges have to add up to the total charge on the molecule. And I think you probably understand that those two have a -1 formal charge based on the last slide there. So that's an increase. Where the heck are we? We're going through this again. Sorry. Are we going forward in our? Okay. This is the one we want to do kind of for real. I want you to talk about this in your group. So I have what is the SO bond in the sulfate ion? So the formula is here. You can see it. It's SO4 -2 ion. So that'll help you draw the Lewis structure. So take a few minutes here. Let's go into our groups, sketch out the Lewis structure. What we're looking for is the bond order. Is it 1, 1.5, or 2? And you'll see right away that you're going to have a choice of Lewis structures, and they will have different bond orders for the SO bond. Which is the best? Settle on that. So I'll start the poll. Hopefully. Okay. Okay, the poll is running. So let's go into our small groups and we'll take a vote. Okay, go ahead, push a button if you haven't yet, and we'll see what you're thinking. Hopefully, we can make this darn thing work for us. 1.5 is more popular than the other two, not more popular than the other two combined. Oh, actually, it's very close. Let's see what you're thinking. I'll give you what I'm thinking for this as well. So the idea is you have to draw Lewis dot structures. So first you have to count up the total number of electrons. So sulfur and oxygen are 6 valence electrons. There's 5 atoms with 6 valence electrons. And you have to add 2 because the whole thing has a -2 charge. So you have to take that 6 times 5 is 30 plus 2 more is 32 electrons and spread them out over the molecule. And here are 3 possible ways to do it. This seems like the best way initially because all the octets are full and you're done. But you don't want to stop there. You say sulfur can expand its octet. Will it help me to expand the octet? Share those electrons. And if you calculate formal charges, it would give you a clue. Yeah, that's a lot of formal charges, and they're spread out all over the molecule. If I share just those 2 pairs, that reduces all those formal charges, and it leaves the -1 formal charges on 2 of the oxygens, and that's more electronegative. If I keep going and share there and really expand the octet of sulfur, the -2 charge is now on the sulfur, the less electronegative element. So the balance between those is this one, just too many formal charges spread out all over the place. That one, the negative charge is on the less electronegative element. So this is the better Lewis structure. And if you draw that Lewis structure, the bond order, there's 1, 2, 3, 4, 5, 6 bonds divided between those 4 bonding locations. So 6/4 or 1.5 is the bond order for the sulfate ion. Great. Okay, so we'll go to now, I think the next thing is the most missed question on the exam. And I hope we can do it correctly. So we'll look at that and do a chem quiz on that. So there were a lot of questions that were missed. This one was missed a lot, and it's interesting. So we'll do this. So you've seen this on the exam. You have this energy level diagram, and you want to predict a, ooh, be careful. Don't touch the board. You want to predict a spectrum. So you want to predict what the emission spectrum is from that set of energy levels. So I will start the thing, and it told me it captured this, and it's running. So go ahead, talk amongst yourselves, and see if you can come up with the solution for that one. Okay, everyone. That was a good discussion. I hope you have chatted in your Zoom rooms and come up with an answer here. We were talking here as we were letting you go here. The rule for attendance got muddy this year. The rule for attendance is you have to respond with your clicker from the Zoom room. And we did not enforce that this semester. It just got muddy. I think what we'll do is start enforcing that. That is, you have to correlate your response from the Zoom room. We keep attendance in both places, basically. It's so important that you're in the Zoom room talking, and there's a lot of silence, reverberating silence in the Zoom room. So I'm going to stop this poll now, and let's see what you are thinking. Ah, my goodness, that's wonderful. Everyone has gone for E, essentially. So we'll take these responses and we will add them to the correct responses, add them to your midterm score. You probably have seen in the gradebook that Lillian did a tremendous amount of work, collected all the grades together and posted raw scores on the gradebook. There's one little thing that we're fighting with. You can get more points on the midterm than it says. It says out of 35. You can get more than that. You could get them all right and this question. So just be aware. It says out of 35, you can get more than 35. Not many. Doesn't apply to many people, but at the end, we'll give you a total readout. I agree with these people who said E. Why is that? Let's go through it. Just be organized. What you want to do is see what transitions are available. So start at the highest level and go to the lowest level, and then highest to next and highest to next, and just draw them out. So there's one transition you can get. There's another transition you can get, and there's another. That's all you can get from the top. And then go to the second level and do all those. So there's two transitions you can get. And then go to the third level and do all those. So there's 6 possible lines you should get in your spectrum. 6 possible photon energies are going to come out of there. And 2 of them are quite high energy and similar. So those there. And then this one here, that's quite a bit lower energy. So I have to come down here. And again, these are schematic. This is qualitative. You can't get exactly right. You can see, okay, that one's about the same as that one. So that's for this. And then from the second level to the ground states, there's 4. This one looks the same size as that one, so I've put it very close, 3 and 5. And then this one, obviously smaller than all of them. So that looks like E. In fact, if they were exactly the same energy and those spacings were the same, you'd look like that. And that is E. Great, guys. Fantastic. So happy you got there. So let's just continue now with our analysis of Lewis structures. You can determine oxidation numbers from Lewis structures. And oxidation numbers are something that we tabulate to determine what's happening when a reaction occurs. Oxidation and reduction, we're going to talk about a lot in the coming weeks. Reduction means reducing the oxidation number. Oxidation means increasing the oxidation number. But we can get them from Lewis structures, so we're going to introduce it here so we can use it later. And it's interesting because to do the formal charge, you did a covalent, you shared the electrons equally. You took all of them in the bonds and said, you have those 2, you have those 2. Here, you divide them up like it's an ionic bond. And you say the electronegative element gets all the electrons in the bond. So in this case, oxygen would get all 4 of those, and this oxygen would get both of those because it's the more electronegative element. That leaves nitrogen with just the two that were in the lone pair. So it's quite a different way to do the accounting. You treat it ionically, but then you can, again, compare it to the valence shell from the periodic table and calculate an oxidation number. And it's, again, just the difference between these two. So oxygen appears to have 2 more electrons, so that's going to be a -2. Nitrogen appears to have been robbed of 3, so it has +3 for its oxidation number. The oxidation numbers, though, also have to add up to the charge on the molecule. So that is something we keep track of, and we keep track of them because this oxidation reduction chemistry is incredibly important it's much more important these days because everything we do is battery powered and battery research. If you're interested in chemistry, now there's a lot of good places to go. Obviously, atmospheric chemistry and fuel chemistry, but battery chemistry. Batteries need some work. There hasn't been an advance in battery technology. Storage of electricity is the biggest problem in the world right now, as far as I'm concerned. We can make plenty of electricity. It's just we can't make it when people need it. So you make it and store it and then use it later would be fantastic, but we can't store it. Batteries aren't that good. And if you need to store enough for a city, how do you store it? Those are the things that the chemists of the future are going to have to come up with. I have a Tesla, and the Tesla Model S, it is powered literally by 5,000 flashlight batteries. I'm not kidding you. They solder together 5,000 flashlight batteries and put it in the car. So it's the same little battery that you put rechargeable in your flashlight is making the Tesla. Come on. We have to do better than that. It's hard. It's a hard problem. But this oxidation reduction, this moving around of electrons, is what makes that chemistry go. And we'll talk about it later. So how does the oxidation number of nitrogen change? So I'll talk through this one with you. So we're going to change the oxidation number going from NO2 to NO3, that chemical reaction. And that is an oxidation you should easy to recognize because you add an oxygen to something. Clearly an oxidation. Iron metal going to iron oxide. That's an oxidation. When you add oxygens to things, oxygen's electronegative, it withdraws electrons, and that causes this oxidation number to decrease because you're taking away those negative charges, and that will go down. And you can see it here, obviously, when you just calculate it. So in the molecule, how do I do the oxidation numbers? Well, I treat it ionically. So oxygen gets all those, that oxygen gets all those, leaves this with 2. When you put the other oxygen on, now that oxygen gets those 2, leaves nitrogen with none. So the oxidation number changes from +3 here to +5. An increase in the oxidation number is an oxidation. A decrease, a reduction in the oxidation number is a reduction. That was easy to remember. In fact, that's how you should remember it. Reduction in oxidation number is a reduction, so an increase must be an oxidation. So there's an, why aren't we getting, there it is. That's an increase in oxidation number. Okay, so let's go on to the shapes of molecules. So Lewis structures don't tell us much about the shape. If I draw a Lewis structure that looks like this, that looks flat and planar. Ethanol, that molecule there, is not flat and planar. Sulfate ion looks flat and planar. It's not. So the Lewis structure gives us an idea of these, the bonding structure, the general architecture, but not the 3-dimensional shape. So it's a topological issue. This fits part of the problem. There's another layer to the problem. How do we address the layer of what does it do in 3-dimensional space? What we need to do first is define something called the steric number. The steric number is you add up everything around the atom you're interested in. The number of lone pairs and the number of bonded atoms. Not the number of bond pairs, just what it's attached to. So here's a stick figure. There's a carbon with 4 hydrogens around it. That steric number is 4 because it has 4 things around it. The steric number of these carbons is also 4. It's obvious. A hydrogen, a hydrogen, a hydrogen, and a carbon. 4 things attached. The steric number of that oxygen is 4. 2 lone pairs, 2 bonded pairs. The steric number of this sulfur is 4. 1, 2, 3, 4 bonded atoms. I don't count up the bonds. I count up the bonded atoms. What we're trying to do is see what's we call the steric number. Steric is a spatial interaction. What is there that's taking up space? The bond doesn't take up space. It's that having that atom, this atom, this atom, this atom, and that atom, those 4 atoms taking up space that determines where they have to arrange in 3-dimensional space. So this gives rise to something we call the valence shell electron pair repulsion theory that says all these valence shells, all these bonded and lone pairs, they just try to get as far away from they can in space from each other. They're stuck around the central atom, but they still got to distribute themselves in space. So VSEPR, some people pronounce it VSEPR for some reason. It's easier to say than VSEPR, I guess. So the VSEPR shapes just come from just a geometric argument. You have things in space. How do I get them as far away as possible from each other? And I think it's probably obvious too, if your steric number is 2, that is you have 2 things, the farthest away you can put them is 180 degrees from each other. So that's pretty clear. So I am the central atom on my chest. I have 2 atoms that I'm bonded to. 180 degrees is as far away as I can get. That's linear. And I don't think it's any surprise if you have 3 things attached. So now my feet will each be an atom. I have to put 1 there, 1 there, and 1 here. And now I have these 3 things, this hand, the hands, and the feet as far away from each other as possible. If I go to 4, so now each hand will be an atom and each foot. I go 1, 2, 3, 4, and you may think square planar. That's the farthest way to get apart. But it is not, because you have 3 dimensions. I can take these 2 and put them in this dimension. And then I have more room to get them farther apart. Use all 3 dimensions. Wait. Dismount. I need a score. The dismount, that arrangement is called tetrahedral. And it looks slightly different here. It looks like I've drawn this little pyramid thing here. I have one here that it looks like the little pyramid thing. The way I was doing it was my legs and my arms. So if you tilt it like that, it looks like this. Okay? And here is our 5 things. Now we arrange them what we call trigonal bipyramidal. So 2 little pyramids, trigonal pyramid attached, trigonal bipyramidal. Now there's 2 different bond angles. The bond angles here are 90, and the bond angles around the edge are 120. All these just have 1 bond angle, 180, 120, 109.5. There's 2 bond angles here. I go to octahedral, 6 things, and 6 things, all the bond angles are 90 degrees again. There's 4 things in a plane, and 1 on top and bottom. All the bond angles are 90 degrees. So we can look at this a little more detail, it's better to have some models here. So let's give you some actual examples. For steric number 2, carbon dioxide, that's linear. Steric number 2, the boron dichloride ion. Here's steric number 3, where I have this methyl ion. Carbon, here's steric number 3. This carbon here. Internet sounds like it has gone down. Are we online? We're still good? Wireless may have died. We have 1, 2, 3 things around that carbon. Steric number 3. So these are all trigonal planar. Steric number 4, there's the ammonia, NH4. The most important one, the steric number 4, is water. Steric number 4, 1 lone pair, 2 lone pairs, 1 atom, 2 atom, steric number 4. But this right now already gets you into a little bit of a quandary, because we're not going to call water a tetrahedral molecule, even though it has that steric number 4. And the reason is the lone pairs, you know, they don't count when you're talking about the molecular shape, just where the atoms are how the atoms are arranged. So how the atoms are arranged determines that. So we call this molecule just a bent one. It's not linear, it's bent, but it has a steric number 4 around the central atom. There's steric number 5, and steric number 5 could be a trigonal bipyramid. Everything could be an atom. Here, 2 of the steric number 5 are lone pairs, so it's iodine trifluoride in a T shape. Take that away, and it just looks like a T. It might be interesting. You might have said, well, why didn't you put the 2 lone pairs top and bottom and make trigonal planar? We'll talk about that later. There are some times when you want to might make a decision about which is the best place to put a lone pair versus a bonding pair. Here's steric number 6, sulfur hexafluoride, or here's steric number 6 on xenon, xenon tetrafluoride. That is a square planar molecule. So we can look at some of these. Since the internet is down, we might have to do it this way. So here's a little molecule builder, and we can look at the various geometries here. So there's a linear, this is steric number 3, and you can fade back and forth now between the screen and me so they can see this. So I can take a lone pair and add it there. And when I add a lone pair, you can see that is a bent molecule with steric number 3. Get rid of that lone pair. I can add 2 atoms bonded, and that is my tetrahedral shape. I wonder if I click this, does it tells me? So there's going to tell me it's tetrahedral in both the electron geometry and shape. The shape of the molecule, the molecular geometry, is going to differ from the electron geometry when there are lone pairs involved. So if I take one of those off and now I have still steric number 4. So my electron geometry, steric number 4, is still tetrahedral, but this molecule is a trigonal bipyramid. Oh, excuse me, a trigonal pyramid, only one of them. Trigonal pyramidal. Now, this is one of those places in chemistry that I dislike, of course. You have to memorize these names. So there's lists in your reading, and there's lists online. I gave them to you there on the slides. We have to talk the same geometry. So you have to be able to say trigonal pyramid is what that is. So I know what you're talking about. We're all speaking the same language. Here's water. So steric number 4 still tetrahedral arrangement of the electron pairs, but you can see water is just a bent molecule with lone pairs. Show bond angles. I like that. 109.5. I'm going to get rid of the lone pairs and put back. There it is. You have to also, unfortunately, memorize these bond angles. So 109.5 is the one you have to remember. That's the tetrahedral. All the others are 90, 120, 180. Those are obvious. 109.5 is the famous tetrahedral bond angle, and they're all the same. Let's just continue. Let's add. So there we are. If I have steric number 5, I have 120-degree bond angles along the planar part and 90-degree bond angles along the axial part. So we have kind of two positions there. I guess I could write that down. Here, that 90-degree bond angle there, we have axial positions. So this is the major axis. So this is an axial position. And we have equatorial positions. So you're on the axis, 90-degree bond angles, or you're on the equator, the equatorial bond angles. So if I shift this here, these are the equatorial bond angles. We give those two designations to keep that straight. And of course, you can add, so let's take away, those could have been bonded pairs. And there you have this situation here where the molecule looks like a little seesaw. It's called a seesaw, but the shape of the electron pairs is trigonal bipyramidal still. And you can play with this. The link is in your notes, so you can play around with these things. I'm going to switch from the models to real molecules, though. And when I go to real molecules, so here's water, so H2O. The models there, I was giving those precise bond angles. So the electron geometry is tetrahedral still here. If I show the bond angles, this tetrahedral angle, molecular geometry, as you know, is just bent here. The tetrahedral angle compresses a little bit when you have lone pairs versus bonded atoms. So the electrons can be held more closely to the central atom, and having those closely can kind of repel these electron pairs in the bonds and squeeze those angles slightly. And you're going to have to know that. The bond angle in water, 104.5 instead of 109, if it were just a tetrahedron, is a famous result, and it's one that we'll expect you to know. So play with that at home. That's a fun one. So let's we'll talk through this one together. In the following acid-base reaction, which species has the largest bond angle? So I have H3O+, NH3, NH4+, and H2O. And this is an acid-base reaction, which we're going to talk about again here in a week or two, and you can choose A, B, or 3, apparently. Where's my 3? So let's talk about this. And I think you know what you have to do. You have to draw Lewis dot structures. You have to get to the best one and then count lone pairs and bonded pairs, get to a steric number. Once you're at a steric number, you know the shape, and then you can tell us what the bond angles are. So I just do that for you here. The steric number for all of them is 4. You'll find out. H3O+, here, NH3, so all I've drawn is the hydrogens here and lone pairs. NH4 plus the 4 hydrogens. So they all have steric number 4, so they all are going to have a tetrahedral electron geometry, but the lone pairs don't count. So these bond angles are smaller because that lone pair on the top squishes those down together. This one is going to be close to 109. These are shorter, so the largest bond angle is the NH4 plus. So which of these has an electric dipole moment? So we will do part of this for you, and then you can weigh in. So which of the following has an electric dipole moment? This methylene dichloride, sulfur dioxide, or boron trifluoride? Excuse me, bromine trifluoride, that matters. If I draw some of the geometry here, you can check. I got this geometry from the Lewis dot structures. If I draw that geometry, which one of those has an electric dipole moment? So let's talk about that in our groups. I started the quiz. If the internet is live, do you guys see it? Can someone try to respond? I'm getting some responses, so I think our internet, our wireless is back on here. Maybe. Yep, drop me in a breakout room. Question is, which has an electric dipole, not which is bigger or smaller. Sorry, you guys couldn't see everything there. So now you can see from your iClicker and this board. Okay, let's come back together and see what you're thinking. Go ahead and take a press a button if you have not yet. So many of us, we're actually pretty spread out. B is more popular. Just looking at it, SO2 sounds linear to me. It sounds like it would not have a dipole moment. And that looks trigonal planar. That doesn't either. But of course, you have to count up electrons and you have to be careful. That's the point of this one, of course. So let's look at it together. So I did the electron pair geometry, and I came up with these structures. So tetrahedral here, SO2, I've removed the lone pairs and have that bent geometry. And here, BRF3, I remove the lone pairs and have that geometry. So is there a way now? The electric dipole moment, if you recall, is all bonds have a little bit of an electric dipole moment. So that is a little vector going from there's a little bit, these are chlorines here, Cl, Cl. So the chlorine is more electronegative than the carbon. So there's a little dipole moment there that points from the positive to the negative. It's a little vector. There's a little dipole moment here along that bond. There's tiny ones. Carbon and hydrogen have a very similar dipole moment, so there isn't a lot of electron polarity there. Those two little pink ones that I've drawn add up to give the whole molecule a dipole moment. So each individual bond you consider, you say, does it have a dipole moment? Which way is it pointing? And then you look at the whole molecule and see, could they cancel each other out? Could they mathematically add to zero? And if you think about it, it's going to be rare that you get a molecule that's symmetric enough that all the little bond dipoles add to zero. It's more common to have a dipole moment than not. You have to be perfectly symmetric. And none of these are perfectly symmetric. So there's a dipole moment there, there's a dipole moment there, and there's a dipole moment there. So all those molecules have dipole moments. So you could have answered A, B, or C there and been right. Which of the following molecules or ions is linear? We'll talk through this one together. So here are our choices. ICl2 minus, BrF2 plus, or hydrogen sulfide, H2S. I can draw the Lewis dot structures. When I draw the Lewis dot structures, I count a steric number. 1, 2, 3, 4, 1, 2, 3, 4. Two lone pairs, two bonding pairs, two lone pairs, two bonded atoms, two bonded atoms, three lone pairs, steric number 5. Then I draw the VSEPR arrangement, and the VSEPR arrangement for steric number 4 is tetrahedral, and for steric number 5 is trigonal bipyramidal. But to get the shape of the molecule, we ignore the lone pairs. We just want to know the arrangement of the atoms that are bonded together. So we don't have to consider the lone pairs here. This molecule is bent. Those lone pairs we don't consider in the molecular shape. So this molecule is linear, 180-degree bond angle. So that's the kind of thing, that's the kind of analysis that takes us from Lewis structure to shape and to dipole. This one, no dipole moment. It's perfectly symmetric. This one has a dipole moment because each bond has a dipole moment. You can tell dipole moment is something I'm more likely to ask you about than the Lewis structure itself, because again, you can Google Lewis structures. I'm going to ask you where the dipole moments are because you have to draw the Lewis structure and think about other things on top of that. So if you're in the classroom and you're on paper, we can have you draw these things, but it's just not a good online exam question to ask you about something that's so easy to just Google. So now we're at the stage where we're drawing more complicated molecules, and we've talked about this already. Molecules can have the same number and kinds of atoms, but there's different ways to arrange them. So just knowing the molecular formula, C2H1, 2, 3, 4, 5, H5O, is not enough to know what the molecule is. This one is ethanol, this one dimethyl ether, but exactly the same molecular formula, simply a different arrangement of the atoms. That's called isomerism. So those are structural isomers where you actually just do different attachments to the molecules in the molecule. The atoms are just physically attached differently. That's easy. Stereoisomerism is where the attachments are similar, but you can still have a different arrangement of the entire molecule. This happens in this case. Here's a famous case because the double bond here makes this molecule planar. And it makes that molecule planar so the chlorines could either be across the plane or on the same side of the plane. So even though all the connections are the same, you can still have isomerism overall if there is a feature of the molecule like this one. So stereoisomerism. Here all the connections are the same, but there's a shape difference, an arrangement difference in space, usually because of some kind of steric interaction. This one has here, now this is a structural isomer of this, because now the arrangements are different. There's two chlorines here. So chlorines are both on the same carbon. So that is a structural isomer of these two. So there's three arrangements, three isomers, two of them stereoisomers, one of them a structural isomer. That has a dipole moment. Oops. This one has a dipole moment. This one does not. So here, the dipole moments are equal and opposite and cancel each other out. Here they cannot. Here they cannot. So that has a dipole moment. So we can see these dipole moments arising from our arrangements. I think I have. Oops, sorry. I think we can look at molecular polarity here. Let's do that. Since I said that's what I'm going to put on the exam anyway. So let's look at the molecular polarity. So here's a little toy where you can change the electronegativity of the various atoms and see what happens to the dipole moment. So here I have atom A and atom C are not very electronegative. Atom B is, so the electron density is up here. So I can put the bond dipoles. So here are the two bond dipole moments pointing towards the more electronegative element. And those add to give you a molecular dipole. And again, I'm sure you're doing this. You can just go back and forth as you feel. Our producer director, Sydney, of course, is giving you the beautiful production. Sometimes you're seeing the board. Sometimes you're seeing me. I'll put the partial charges up there too. So we use these little delta symbols. I'll get rid of the other stuff to make it obvious. Here's the delta. Partial charge, partial plus, partial minus on that guy. I can change the structure here, and now the dipoles are still there. Does the molecule have a dipole moment? No, because now these two cancel each other out. We can turn on an electric field. That's fun. Turn an electric field. This molecule does not react to the electric field. So now there's plus minus, but it doesn't react because it has no dipole moment. But if it does have a dipole moment, two ways to give it a dipole moment. I could change the bond angle, or I could change the electronegativity on one of them. Let's do that. Now, one of the dipoles is bigger than the other, and that molecule orients itself in a magnetic field. Or I could have changed the bond angle, and now that molecule has a dipole moment. Okay, that's another fun one to play with. It's in your notes. You can have fun with that. Now, there's a special kind of isomerism. We're not going to belabor this too much in Chem 1, but it's so important that I have to tell you about it. You can have a special kind of stereoisomer. So stereoisomer, all the attachments to all the atoms is the same, yet it has a different steric arrangement. You can detect a different steric arrangement. A very special subtle one, the pairs are called enantiomers. So here's a carbon with 4 different things, say, attached to it. And that's how you find chiral isomers, these are called. Chirality exists when you have one central atom with 4 different things attached to it that potentially has an isomer. So here, I've drawn the molecule again, okay? And I've drawn it such that it looks like the mirror image. So these molecules are so similar that they're mirror images of each other. So all the connectivity is the same, but those two molecules are not exactly the same. And I bring this up. Well, let's go through an animation. Well, let's do it. Let's do it for real. I have this here, and can you get us a reasonable shot? We have a reasonable shot of this. So here's that molecule in the mirror. So I have that molecule and its mirror image here. But through the magic of Chem 1, I can actually reach behind the mirror and pull that molecule out from the mirror. So now I have the mirror image in my hand, and look what happens if I take this molecule and try to overlap it with this molecule. You can see what happens. They are different. The purple and the green are in different locations. So there's this subtle structural isomerism that's very important because it persists in all of biology. You know that our biological molecules are catalyzed reactions in our body, and it matters exactly where the I'll turn off the autofocus. We probably have to do it again. Maybe we do. I'll turn it off just to make sure. It matters where the positions of those guys are. If you have an enzyme that's coming in and it's expecting to see the blue one here and the yellow one there, it has to be exactly there, or you can't catalyze the reaction. So you can't have the other stereoisomer, even though they're identical in every other way. We define them like we define your hands. Your hands have this property. They're mirror images of each other, but you cannot overlap your hands exactly. You have to put them opposite side to opposite side, same side to same side. Your hands are chiral. So we define them like we define hands. We give a left and a right, the Latin word for right, L and D, levorotatory and dextrorotatory. It refers to how they interact with light, actually. But a left-handed and a right-handed molecule. And this animation will just do the same thing. I'm going to rotate that one 180 degrees. And when I do that, and it does not overlap with this one. So it behaves just like your hands. They look the same, but they're slightly different. And I just want to emphasize that the amino acids in your body that make up your proteins, they are all left-handed amino acids. And you can't live with the right-handed ones because, in fact, you can do this. You can make, in laboratory, you can make anyone you want. But you could take a laboratory mouse and feed them the protein with the right-handed amino acids. And it'd be able to eat and do everything, but it would eventually die because it can't process, even though it's exactly the same, it can't process those amino acids. I don't remember, and you can Google this. I think that there are laboratory rats that they have grown, and they have them so they're all right-handed protein rats because they can just gradually feed them these things. I should have looked before a class. Sorry. Your DNA helices are right-handed helices. You could wrap your DNA in the left-handed sense, but only the right-handed sense exists in nature. That gives you a major and a minor groove, a fat groove and a thin groove of DNA. So that's just a beautiful feature of nature, has to do with isomerism and chirality, chiral molecules in your body. Actually, recent research, I just read about this recently. There are, it turns out, quite a few right-handed amino acids in your body. Back when I was in grad school, we were thinking, well, there's virtually no right-handed amino acids in your body. It turns out there are quite a few, and they're in pockets, usually near nerve centers and endocrine centers. So some of you, many of you, I think are going to go into microbiology or molecular biology. That's a cool thing to study. What the heck are those doing there? And they have a function and they end up there. So there's an enzyme that can catalyze the conversion between left and right. Those exist. We know about those. And they're working in there, and they're making the rights in specific places, and they're sorting out the enzymes and the amino acids. Super intriguing. I will read more. I hope you will read more. We're not going to bother too much with chirality other than to not acknowledge it exists, and it's an important part of biology, so you should be aware of it. You can determine, here are 3 structural isomers of this octane. So they have the same number and kinds of atoms, but they're arranged differently. One of them is chiral. And it's actually easier to determine than you think. You just look for 4 different things attached to a carbon. That'd be 4 different things. And you have to make sure, you have to count the number of chiral centers. So if you find a carbon with 4 different things, that's a chiral center. But just like dipoles, if you have another chiral center, you could offset that, and the entire molecule might not be chiral just because you have chiral centers. But if you have a single chiral carbon in a molecule, then the whole molecule is chiral. And you can find it. It's this one. That is a carbon with 4 different things attached. I didn't draw all the hydrogens, but this carbon here has a 1 carbon chain, a 2 carbon chain, a 4 carbon chain, and a hydrogen attached to it. So this molecule is chiral because it has 1 chiral center. Okay, so we're going to dive into bonding now. So we've done all this kind of hand-wavy bonding thing. So we've taken Lewis structures to the furthest extent we can, and they are useful. We can see already the power of the Lewis structure, moving dots around. But it is not how atoms and molecules work. The electrons behave quantum mechanically, and they exist in standing waves, orbital functions about the atoms. We said that in detail. Well, the same thing is true in molecules. So we want to take our atomic quantum theory and expand it to a molecular quantum theory, attach it to molecules. We're going to do it in a relatively simple way. We're going to say covalent bonding occurs just the way we think it does. You have an atom here, an atom here. It has orbitals. So there's standing waves of electrons here. There's standing waves of electrons here. To get the wave function for the whole molecule, we're going to do the very simple thing. We're just going to take the wave functions, the orbitals on this one, and add them with the orbitals on this one. So mathematically, on the surface of it, really simple. Take a 1s wave function here, take the mathematical form, add it to the 1s on the molecule next to it to get 2 atomic orbitals, making a molecular orbital. So in principle, very similar, or very simple. And you know that I was telling you all this stuff about the phase of the wave function. These are the wave function squared. And when you square the wave function, you lose that amplitude, positive or negative amplitude information. So we put it back by coloring the wave functions. The blue part is positive, the red part is negative. That's the sign of the wave function. We need to know that because you know if you add wave functions, we can do it in pictures. We've done it already. We added simple one-dimensional wave functions, and you get constructive or destructive interference. Well, now we're just going to do that in 3 dimensions with the atomic orbitals. We're going to bring them close together, add the wave functions, and say, well, would you get constructive or destructive interference? And I think you can say, well, I bet if you get constructive interference, that makes a bond. And if you get destructive interference, it does not. So if your electron density goes to 0 because you got destructive interference, that is not going to hold those 2 elements together. But if you get constructive interference and you get a high electron density between those 2, that is going to hold the atom together, or the molecule together. And we're going to add them with pictures. So here I have 1s plus 1s, and I've made that molecule, and I have constructive interference because I've drawn these in green. That means the wave function is the same sign everywhere, and it's a 1s orbital. It can only be 1 phase plus. And when I do that, I actually get an orbital that's lower in energy than the 2 1s's themselves. And that's kind of why bonds form. This wave function has a lower energy than the two S's. And so that is the favorable place for the electrons, those two electrons, to arise. So we call these sigma orbitals now, and that sounds a lot like S. So a sigma orbital is a sum of atomic orbitals. It's a molecular orbital that's a sum, it's a special kind of sum, a linear combination. If you know some math, linear combination just means add them up or subtract them. Add them with constant coefficients, and those coefficients can be plus or minus. So you can add or subtract your orbitals, get a linear combination, and that gives you your molecular bonding orbital. Here's a general principle we have to apply, though. You have to conserve the number of orbitals when you make molecular orbitals from atomic orbitals. And that should make sense to you because that's conserving mass. You can't bring in 2 electron orbitals and form 1 molecular orbital. You need to form 2 to keep that mass balance in place. So how do we accomplish that? Well, we just take 2 different linear combinations. We take the linear combination where we add them with constant coefficients, and then we reverse the sign. So here's antiphase. That's the opposite sign of the wave function. And if I add those together, then there's destructive interference between the 2. That doesn't help you. We make that orbital because we have to conserve the number of orbitals. That one just doesn't help us. The electrons don't go here, they go here. This orbital is available. It's called an antibonding orbital. We give it the symbol sigma star. But the electrons don't go there. It's higher in energy than the sigma bonding. So there's this sigma star antibonding orbital that also forms. So these 2 orbitals are drawn here and here on an energy level diagram. Once you make these 2, then these 2 are gone. You don't have these anymore. You've taken your atomic orbitals and you've made them into 2 molecular orbitals. And here's the energy level diagram. And remember, this is just energy level diagram, simple thing. We have 2 molecular orbitals here. These are our molecular orbitals made from these 2 atomic orbitals, 1 on each atom, and those go away because they've been used to make these 2. So the molecule has 2 orbitals now. The atoms don't have 1s orbitals anymore. They're combined to form sigma and sigma star molecular orbitals. Okay. So then if these 2 atoms were hydrogen, and they could be any element, you would have had an 1s electron in each of those. You have to take those electrons and put them in your new orbitals. And I think you'll guess right away, of course, they go down in hydrogen molecule. The 2 electrons, 1 from each hydrogen atom, goes into the sigma bonding orbital, and H2 is a molecule that exists. It's stable. This is why it has 2 electrons in a lower energy orbital than they could have been when they were hydrogen atoms. You ask, is hydrogen itself paramagnetic? Yes, hydrogen atoms are paramagnetic. Hydrogen molecules are not, because all the electrons are paired. So I go from paramagnetic, the hydrogen H2 is dimagnetic. It is all paired electrons. And we can keep doing this. Let's look at helium. Let's say we added the 1s's for helium. Well, the same thing is going to occur, but I have more electrons from the atoms. So now I have to say I can't use these anymore. I have to use these molecular orbitals, but I fill them the same way. I start at the lowest and I add spin up, spin down, and then go to the next highest and go spin up, spin down. And you'll put H2 molecule, spin up, spin down, spin up, spin down. Use those 4 electrons, 2 from each helium atom, in your helium molecule. But you get to a kind of undesirable result. This arrangement, you have high energy and low energy orbitals, and they're all full. And this arrangement isn't any more favorable than this. In fact, it's worse. I haven't drawn it exactly right. This antibonding orbital is actually higher in energy. So this is not as symmetric as I've drawn it. So having 2 electrons here and 2 electrons here is worse than having them as atoms. He2 does not form molecules. Helium does not form a dimer. It stays as atoms. So already our pictorial idea is already predicting what happens in nature. If I went to lithium, then I would add and subtract the 2s valence orbitals. Adding the 2s, I get a sigma bonding orbital from the 2 2s's added in phase, and a sigma antibonding orbital from the 2 2s's added out of phase. And they're still s's, so it's easy. But the lithium dimer would have 2 electrons, 1 from each lithium atom. The beryllium dimer would have 4 possible electrons, 2 from each beryllium atom. This one has the potential to form a stable dimer. The beryllium doesn't. So this idea of drawing molecular orbital diagrams from atomic orbitals is the formalism we're going to use to describe molecules quantum mechanically. It's relatively straightforward pictures, and we're going to add pictures all the time. So we'll go through this together. Which of the following atomic species is more stable if you ionize it? Remove an electron from hydrogen, helium-2, or lithium-2. So now you can draw the molecular orbital diagrams. You can do that now because you understand how it works. The hydrogen, the 2 1s's add to give you a sigma and a sigma star. The helium, the 2 1s's, still give you a sigma and a sigma star. In lithium, you're adding the 2 s's because they're the valence shell, and you get a sigma bonding and antibonding orbital, and then put in the atomic electrons to the molecular orbital diagram. So pull them out of the atomic orbitals because they don't exist anymore, put them in the molecular orbitals, and you get this kind of arrangement. These are the neutral species. If I ionize them, so the bond order in the molecules, that's bond order 1. So how do you get the bond order from this? Well, you take all the electrons in bonding orbitals and divide by 2. 2 electrons makes a bond. So all the bonding, 2 bonding orbitals divided by 2 is 1 bond. How do I get the bond order here? Well, bonding, there's a bonding orbital there, but the antibonding electrons cancel them out. So take bonding electrons minus antibonding electrons and divide by 2 to get the bond order. Lithium, also going to have bond order 1. Now I ionize. Take 1 electron out, He+. Now my bond order has dropped to 1/2. 1 electron divided by 2 is the bond order there. Here I have 1, 2, 3 electrons, so it's bonding electrons minus antibonding electrons. So it's 2 minus 1 is 1, divided by 2 is 1/2. So that bond order increases when we ionize it. So He2+, the ion, is more stable than 2 He atoms. And you can make that in the gas phase in the laboratory. And here, lithium, it does the same thing hydrogen does. You ionize it, and its bond order, its bond strength goes down. So the bond strength, the bond order increases for hydrogen when you ionize it and decreases for lithium and hydrogen. Helium, increase in bond order. Lithium, hydrogen, decrease upon ionization. Okay? Perfect. We'll meet again tomorrow. and continue our discussion of molecular orbitals.